Greenland's hidden ice lake explodes in rare upward flood. Scientists shocked? Imagine water defying gravity, surging upward through a massive ice sheet with the force of a natural disaster. That's exactly what happened in Greenland, and it's left scientists both baffled and intrigued. But here's where it gets controversial. Could this be a sign of something much bigger happening beneath the ice? In a jaw-dropping discovery, researchers found that a hidden subglacial lake in Greenland burst through tens of meters of ice, sending colossal blocks as large as 5-story buildings flying upward. The resulting floods scoured an area nearly twice the size of New York's Central Park, leaving behind a smooth, icy scar. This event, published in Nature Geoscience, challenges everything we thought we knew about how water behaves beneath ice sheets. It's extremely surprising, says Winnie Chu, a geophysics expert at the Georgia Institute of Technology. For meltwater to force its way upward like this, the conditions have to be just right, almost impossibly so. This isn't your typical water flow. It's a rare explosive phenomenon that raises more questions than it answers. The event, which occurred in 2014 near Glacier in northern Greenland, went unnoticed until a decade later. Mal Macmillan, a professor at Lancaster University, stumbled upon it while analyzing satellite imagery for subglacial lakes. We expected to see a lake draining, Macmillan explains, but what we found was a fracture zone downstream, something we never anticipated. Beyond this zone lay 6 square kilometers of ice, wiped clean by a deluge so powerful it released 90 million cubic meters of water in just 10 days. That's equivalent to the water flowing over Niagara Falls in 9 hours. And this is the part most people miss. Subglacial lakes like these play a critical role in Greenland's ice dynamics. They form when surface meltwater drains downward, getting trapped between ice and bedrock. Occasionally, they empty rapidly, acting like lubricants that speed up glacier movement. But their small size has made it difficult to account for their impact in climate models. Until now, the flood didn't just stop after bursting upward. It drained back under the ice sheet, possibly reaching Glacier. Coincidentally, or perhaps not, the glacier experienced a massive calving event during the same 10-day period, with a chunk of ice breaking off into the sea. The glacier's flow rate also changed unusually that summer, suggesting the flood had a direct impact on its behavior. This discovery adds a crucial piece to the puzzle of how ice sheets function, says Robin Bell, a polar geophysics expert at Columbia University. But the bigger question remains. How does this fit into the story of Greenland's rapid warming? We need to find out if this has happened before, Macmillan adds. It could change how we predict ice sheet behavior in a warming world. Here's where you come in. Do you think this event is a one-off anomaly, or a sign of accelerating changes in Greenland's ice? Could it be linked to climate change, or is it just a natural, rare occurrence? Let us know in the comments. This is a conversation that needs your voice. If you're as fascinated by this story as we are, consider supporting science journalism by subscribing. You're helping ensure that groundbreaking discoveries like this continue to see the light of day. Together, we can uncover the mysteries shaping our planet's future. Greenland's subglacial flood outburst, a new threat to sea level rise. The Greenland ice sheet has been undergoing dramatic changes, losing an average of around 169 billion tons of ice per year over the last 30 years. This staggering loss has contributed roughly 14 millimeters to the rise in global sea levels. Here's what most people overlook. About half of this ice loss is due to processes happening right on the ice sheet's surface, mainly from enhanced melting and the resulting runoff. With Arctic temperatures climbing steadily, we expect surface melting in Greenland to intensify both in scale and duration, which will accelerate ice loss even further. This not only impacts how much water is released, but also increases the liquid water present on top of, within, and beneath the glacier. Understanding how meltwater travels from the moment it forms on the surface until it finally reaches the ocean is crucial. It helps us predict Greenland's future contributions to sea level rise and the cascading effects on the Arctic environment. We know that meltwater, created from melting at the surface, can penetrate the glacier through vertical shafts called moulins and through crevasses, reaching the glacier bed. Studies primarily from southwest Greenland reveal that the underground drainage system beneath the glacier responds quickly to changes in water input. Importantly, the timing and flow of subglacial water can directly influence how the ice above moves. But here's the part many miss. The water flow isn't just steady and continuous. It can also be episodic, taking different routes on the surface, through the ice crystal structure, in glacial, or beneath the ice, subglacial. Along the way, some meltwater gets temporarily stored, which alters ice dynamics, temperature distribution, how the ice interacts with the ocean, the circulation within nearby fjords, biological productivity, and how sediments and nutrients are transported into the ocean. One mysterious and recently discovered element of Greenland's hidden water system is its network of active subglacial lakes. These lakes sit beneath the ice sheet, primarily fed by surface meltwater that has traveled down to the base. They have a powerful potential to suddenly release large volumes of water, dramatically reshaping the channels beneath the ice and impacting the movement of ice around them. Despite their significance, direct observations of these lake drainage events are scarce, and our understanding of what triggers them or their effects remains limited. What's more, the temperature of the ice at the bed, a critical factor influencing how water moves underground, remains largely unknown over much of Greenland's interior. As melting increases with climate change, the frequency and extent of these subglacial lake drainage events are expected to grow. In this article, we showcase new observations from North Greenland, near the marine terminating Harder Glacier, where we detected a previously unknown subglacial lake. High-resolution digital surface models and satellite imagery reveal a dramatic event in the summer of 2014. Over just 10 days, a 2-square-kilometer area on the ice surface dropped by an astonishing 85 meters, creating a deep surface collapse basin roughly 25 kilometers inland above slow-moving ice. Prior to this event, this area had actually been rising, forming a dome-shaped bulge 10 to 15 meters higher than the surrounding ice. After the collapse, the ice within this basin lifted again, before sinking about 10 meters between 2017 and 2019. This dynamic pattern strongly suggests the presence of an active subglacial lake beneath the ice, similar to those observed in Greenland and Antarctica. Imagine the volume of water released. By approximating it as equal to the volume of ice displaced by the new collapse basin, we estimate around 90 million cubic meters of water drained from this lake during the 10-day period. Remarkably, a neighboring surface lake also drained simultaneously, suggesting a direct connection between the surface and subglacial water systems. Modeling shows that the lake was primarily fed by local surface meltwater, with over 99% of the water coming from melting within its catchment area, and 73% generated within just 2 kilometers of the basin itself. During this drainage period, the water discharge averaged 100 cubic meters per second, likely peaking much higher if the flow was concentrated in a shorter time frame. To put this in perspective, this outflow was approximately 100 times greater than that of a similar-sized Antarctic subglacial lake, and is one of the largest subglacial lake drainage events recorded in Greenland to date. Even more shockingly, this drainage rate was about 30 times larger than the total daily meltwater runoff from the entire Harder Glacier catchment at the time, indicating a major disturbance to the glacier's underground water system. But here's where it gets controversial. Conventional understanding holds that subglacial floods route water beneath the ice according to natural gradients in hydraulic potential, meaning water flows along the bed steadily toward the ocean. Yet, in this case, evidence shows a very different phenomenon. About 1 kilometer downstream from the collapse basin, a new fracture zone formed on the ice surface, marked by huge fractures and blocks of ice up to 40 meters tall. uprooted and chaotic. Beyond this fractured area, a 6 square kilometer region had its ice surface scoured clean. These observations suggest that a huge volume of water actually forced its way upward, breaking through the ice surface in a powerful outburst flood that briefly flooded the glacier's top surface. The forces were strong enough to push water vertically through cold, thick ice. Analysis shows that the water's pressure was sufficient to reach the surface at this fracture zone. This is striking because it challenges the traditional one-way plumbing model of ice sheet hydrology. Further, analysis of the glacier's strain rates indicates a shift from compressing ice to stretching ice right at this fracture location, which may have helped cracks propagate upward through the ice column. What's even more fascinating is looking back over satellite imagery spanning 36 years that reveals this distinct oval-shaped feature linked to the subglacial lake has existed since at least 1985. Only one earlier drainage event is apparent in 1990, but unlike in 2014, that event did not cause any surface fracturing downstream, indicating the water must have stayed subglacial and not burst through the ice surface. This makes the 2014 Outburst flood truly unique in the observational record. Downstream, the scene is equally intriguing. The flood-scoured region abruptly stopped, where a surface lake also drained simultaneously, implying the floodwater, after bursting onto the surface, flowed across it, and then plunged back below the glacier, before continuing beneath the main trunk of the harder glacier to the ocean. This synchronous surface and subglacial lake activity suggests the surface flood likely triggered the superglacial lake drainage, possibly via a rapid cracking process at the lakebed called hydrofracture. Moreover, just days after this event, the main glacier terminus experienced a massive calving event, with the ice front retreating 500 to 600 meters, the seventh largest in over 3 decades, though it's still unclear if there was a direct link. Could this sudden release of floodwater have altered stresses at the glacier front or intensified ocean melting beneath the ice, leading to such a calving event? The possibility certainly sparks debate.